Hello everyone, welcome to my fourth video on L'Hopital's rule, and here we're going to look at case 4 indeterminate forms. These are indeterminate forms which we call special cases. So they are the form 1 to the infinity, 0 to the 0, or infinity to the 0. There's other forms that resemble these ones here, but these are the main three that we're going to be using in this video. And let's take a look at the strategy. So notice that over here we're dealing with exponentials. So the strategy that we have to apply are actually a log property. We're going to apply the log property. B to the x is equal to e to the ln of b of x. So notice that e and ln cancel each other, leaving us with b to the x. So whatever is here essentially just goes into the bracket of the ln. And the last property for logarithm, if we jump into the exponent, notice that we could take the exponent x and sit it in front of the ln. And that's what we get here. We get this thing here is equal to e to the x times ln of b. So notice the exponent of the x drops down in front and multiplies. Why do we do this? Well, we're going from a case 4, and by jumping into the exponent and ignoring the e, we now have a multiplication, which is a case 2 L'Hopital's rule. So we reduced it from case 4 to case 2, and then from case 2 we'll reduce it down to case 1. So let's take a look at a couple of examples, and make sure you have this property memorized, because we're going to apply it every time we're dealing with a case 4 indeterminate form. Let's go and practice. So in this first example over here, it's asking us to use L'Hopital's rule to evaluate the limit, and the limit that's given is the limit as x tends to 0 from the positive side of x to the exponent sign of x. So we begin by evaluating the limit, replacing x with 0, giving us 0 to the exponent sign of 0 is 0. So this is the indeterminate form 0 over 0. This is our case 4. Let's go ahead and apply our property. So we know that b to the x is equal to e to the x ln of b. That was the property that we saw earlier. Let me write it just to remind ourselves on top. So b to the x equals, at the end of the day, e to the x times ln of b. Okay. So here, instead of b to the x, what we have is x to the sine of x. So we're going to rewrite this limit as x goes to 0 plus. So the base b is the x, and that's going to be inside the ln. So we're going to rewrite it as e to the ln. Or maybe let's do it in two steps. So e to the ln cancel each other, so this is equal to x to the sine of x. Right, so I took exactly what I started with and I put it into the bracket of the ln. Okay, so this is all in the exponent of the e. So e to the ln essentially cancel, and we're left with just x to the sine of x. So this and this is equivalent. Okay, using this property up here. Right now I have it in this form. Okay, and we could drop the x on the next step. We'll do it in two steps. So we'll drop, instead of the x, it's whatever's in the exponent, so we'll drop the sign of x in front, giving us limit as x tends to 0 from the positive side of e to the sine of x times ln of x. Okay, so this is the idea. So this is our first property. We applied this, we got it in this form, great. Now what do? The idea is to take the limit, since e is exponential, those are continuous functions. And one of our properties from limits that we saw at the beginning of the semester is that if this is a continuous function, the limit could just ignore the e and jump straight into the exponent. So we could just focus on the exponent, okay? Take the limit of just the exponent and we'll call that L. So this is equal to e to the exponent of the limit as x goes to 0 from the positive side of sine of x times ln of x, okay? And we'll call all this here L. So this is equal to e to the L. Okay. The reason why I'm doing this is because our goal now is to focus just on the exponent. And this is super important. Don't forget that we're just getting the answer of what's in the exponent. Okay, this is not our final answer. So let's go ahead on the side now and continue from L. So L tells us we're taking the limit as x approaches 0 from the positive side of sine of x times ln of x. Okay. So this is like side work now. We're pausing from this. Okay. And we're going to solve this piece here, just L. We're focusing just on the exponent. So we have a multiplication, and we know if we have a multiplication, that's case 2. We're replacing it with 0. We get sine of 0, which is 0, and ln of 0, which is negative infinity. 0 from the positive side is negative infinity. So this gives us case 2, 0 times negative infinity, which means we have to flip one of the functions. Okay, so the one we could flip is either ln or sine. I'm going to go ahead and flip the sine. And we're dealing with ln of x over, instead of sine, I'm going to deal with cosecant. Okay. So we have ln over cosecant. And now we have, if we substitute 0, we have infinity on the top, negative infinity on top. Substituting over here with 0, we get negative infinity over infinity. So we could apply L'Hopital's rule, because we have the form negative infinity over infinity. Okay. Taking the derivative of the top and the bottom, we get limit as x goes to 0 from the positive side. Derivative of ln is 1 over x. And the derivative of cosecant, well, remember, the derivative of secant is secant tan. The derivative of cosecant, since it starts with a c, this is the trick that was given, it's going to be negative. And the derivative of secant is secant tan, so the derivative of cosecant is cosecant cotangent, with a negative because it starts with a c. So negative cosecant x times cotangent x. Okay. So let's go ahead and simplify this. If we substitute right away negative cosecant with 0 and cotangent with 0, what do we get? This is equal to the limit as x goes to 0 from the positive side, 1 over x, over, this we can rewrite it as negative, what? Negative 1 over sine times tan. And by flipping it, we get, I'm running out of room, so I'm going to have to erase here on top. Just remember, we're still working on the exponent. We get up here, limit as x goes to 0 from the positive side. I'm going to flip this at the same time, giving us sine x times tan x over x. Right? If we multiply by the reciprocal, this guy comes on top, this is on the bottom. Okay, so this continues up here. And now from this, we take the derivative. If we substitute 0, we get 0 over 0. So we could apply L'Hopital's rule again. And we get the limit as x goes to 0 from the positive side. Here we have a multiplication, so we apply product rule. So the derivative of sine is cos. Leave the tan, plus the derivative of tan is secant squared, and leave the sine. All this over derivative of x, which is 1. So that's reassuring, because now we know we won't get an indeterminate form because the denominator is 1. So whatever we get on top is our answer. So substituting with 0, we get tan of 0, sine of 0, the whole top is 0. So we get 0 over 1, which is equal to 0. If you stop here, your answer is incorrect, so be very careful. This is my warning sign to you. This is not the answer. Okay, so it's common for students to stop here. Why isn't this the answer? Well, what did we solve for here? We solved for L. And what was L? I erased it now, I don't have it on the board, but L was what was in the exponent. Remember, we still had the base E. So what we showed here is that L equals 0. But what you have to do is go back to what I erased, so I don't have it on the board, but go back to the part where we had e to the L. Because what we found now is L is equal to 0, so this is like continuous. Pretend I didn't erase. We continued from the e to the L that I had written over here. And our answer, our actual final answer, is e to the 0, which is 1. So the limit of x to the sine of x, which is 0 to the 0, is actually 1, okay? Don't put 0. This is our final answer. So be careful for that. It's a very common mistake for students to stop too early and assume this is the answer. You have to remember that we're focusing on the exponent. Once you get your answer for the exponent, you're not done. You plug it back into the exponent of the e, and this is in fact the final answer. Okay, let's keep practicing. So in this next example over here, example number 2, it says to use L'Hopital's rule to evaluate the limit, and the limit that's given is the limit as x tends to 0 from the positive side, cos of x to the exponent x to the negative 2. So pause the video, try to solve this on your own. Again, watching someone else do math doesn't help you improve. You really have to sit down, do the work, practice the problems, okay? So we have to first evaluate the limit. So the first thing, we replace the x's with 0, giving us cos of 0. Cos of 0 is 1. and to the exponent 0 to the negative 2. So x to the negative 2, think of it as 1 over x squared. And if we're substituting x with 0, this is 1 over 0, or a number that's really close to 0. When you're dividing by a very small number, it makes the whole thing big. So extremely big, it goes off to infinity. So we have the indeterminate form 1 to the infinity. Let's go ahead and evaluate it. So we begin by applying our property. So we have the limit as x tends to 0 from the positive side, cos of x to the exponent x to the negative 2. We introduce the ln. So we raise it to the e, put everything in the ln, and we get ln of cos of x to the exponent x to the negative 2. And next we drop the exponent x to the negative 2, not in the front there, sorry, the x to the negative 2 in front of the ln, still in the exponent. So limit as x tends to 0 from the positive side, e to the x to the negative 2 times ln of cos of x. Okay. And now again, e is continuous. E is an exponential function, it's continuous. So we could take the limit, our limit properties tell us that we could take the limit and then jump straight into the exponent. So we're going to ignore the e and take the limit of just what's in the exponent, okay? And we'll call this guy L. So we'll call it e to the L. So this is work we have on the side. We're going to jump away from this and focus just on the exponent for now. So we know that L is the limit as x tends to 0 from the positive side of x to the negative 2 times ln of cos of x. If we substitute 0 at this stage, we get 0 to the negative 2, which we saw earlier was infinity, times ln of cos of 0. Cos of 0 is 1, ln of 1 is 0. So we have infinity times 0. So this is a case 2. So we reduced it, or we focused on the exponent, which is just a case 2 L'Hopital's rule. Now that we know this is case 2, we have to flip one of the functions. Which functions are we thinking of flipping? The x to the negative 2 or the ln of cos? Well, I think it's obvious, but I'm going with the x to the negative 2 because when I bring it down, it's going to be x squared. And when you take the derivative twice of x squared, it's going to disappear. So that's my game plan. If you wanted to bring down the ln of cos of x, and this is like your attempt, it might work, I don't know. So go ahead and try it. If it works, great. If not, you chose the wrong function, go with the easier one. So let's go ahead and do this. So I'm going to write this as limit as x tends to 0 from the positive side, ln of cos x over x squared. And now we have the indeterminate form. Here we have 0 squared, which is 0. Ln of cos of 0 is 1, and ln of 1 is 0. So we have 0 over 0. So now we could apply L'Hopital's rule. So we write our symbol h with the hat, L'Hopital's rule 0 over 0. That's the type of indeterminate form we're dealing with. And now we write the limit. Okay. So we take the derivative of the numerator and denominator individually. So the derivative of ln of cos is 1 over cos. So think of it as ln of x, 1 over x, so 1 over whatever's in its bracket, times the derivative of what's in its bracket. So derivative of cos is negative sign. Okay. On the bottom, we're taking the derivative of x squared, which is just 2x. And I'm going to simplify the top. So on the top, notice we have sine over cos, which we know is tan. So this is just limit as x tends to 0 from the positive side of negative tan x on top over 2x. You don't have to do it this way. This is just the way I'm seeing it. And now we evaluate it at 0. So we get tan of 0, which is 0, and 2 times 0 is 0. So we have L'Hopital's rule again. We have the indeterminate form 0 over 0. So let's apply L'Hopital's, giving us the limit as x tends to 0 from the positive side. The derivative of negative tan is negative secant squared. And the derivative of 2x is just 2. Now if we evaluate the limit, we substitute the x with zeros, we get negative secant squared of 0. Secant squared of 0 is just 1, giving us negative a half. And we're done. This is our answer. So if you got negative a half, that's wrong. Be careful, you're not done here. This is a common mistake. Students stop too early. Okay, the answer you found here corresponds to L, the limit of what's in the exponent. So you always have to come back to what we started with here. The problem that we're asked is to solve this limit, not just L. So you found the limit, the exponent of the E. So your answer is not negative a half. Your answer is e to the L, And we know L is negative a half, so it's e to the exponent negative a half. Okay, so be very careful here. And e to the negative a half, we don't want negative exponents. We could write it as, let me just erase to give me some room. So we jump back up here. We write e to the negative a half. We don't want negative exponents in our answer, so we'll write it as 1 over e to the half, which is equal to 1 over square root of e. This is, in fact, the right answer, not this one. This is partly. This is the halfway mark, let's say. This is the answer for the limit, and this is the actual final answer for this limit over here. So notice that if you have 1 to the infinity, so 1 times 1 times 1, infinite times, it doesn't actually just stay at 1. When we're talking about limits, it might converge to an actual value, which is not 1, okay? So be very careful. In this case here, we get 1 over square root of e, and that's the final answer. Let's keep practicing. So the following example is very nice. We're gonna see why once we get the solution. So we use L'Hopital's rule again to evaluate the limit, and the limit that we're dealing with is limit as x tends to infinity of 1 plus 1 over x to the exponent x. This should look familiar. I'm not gonna mention it now, I'll state it at the end. So I'll let you pause the video, try to solve it, and see if you get the same answer as I do. So the first things first, we evaluate the limit, substitute x with infinity. So 1 over infinity is 0, 1 plus 0 is 1, and infinity in the exponent. So we have the indeterminate form, 1 to the exponent infinity. We have case 4. Let's go ahead and apply our log property. So let me right away do it. Limit as x tends to infinity. I'm gonna write e to the ln. We copy what's in the bracket. 1 plus 1 over x to the exponent x. Okay, so essentially we just recopy what we have here into the bracket of the ln. And now we use the property where we drop the exponent in the front, giving us limit as x tends to infinity, e to the x times ln of 1 plus 1 over x. Okay. So again, e is continuous, so we're going to focus on the limit of what's in the exponent, and we'll call that e to the l. Okay. So this is our side work. We'll come back to this later. Let's focus on the exponent L. So L equals the limit as x tends to infinity of x times ln of 1 plus 1 over x. Okay. What type of indeterminate form do we have here? Well, we're replacing x with infinity. So we have infinity times 1 over infinity is 0. ln of 1 is 0. So we have infinity times 0. We have a case 2 indeterminate form. So since we have a case 2, we have to flip one of the functions. Again, here I think it's obvious, but if you're flipping the ln, that's I think a bit more difficult. I would go ahead and flip the x. Okay. Why? My reason being is if I leave the ln on top, if I take the derivative of the ln of 1 plus 1 over x, the derivative of ln is 1 over x. So I'm not going to have a logarithm anymore. That's why I want to keep that on top. I don't want to bring it on the bottom. So that's my game plan. Let's go ahead and try it. If you did it the other way, you should still get the same answer. You might get stuck. I would bring down the x. So that's the way I'm going to go ahead and solve it, giving me limit as x tends to infinity, ln 1 plus 1 over x to the negative 1. Okay. And what's in the bracket, instead of thinking of it as 1 over x, I'm going to think of it as x to the negative 1. Okay. So when we're evaluating the limit, we have 1 plus x to the negative 1 is 1 over x. So 1 over infinity is 0. This piece is 0. 1 plus 0 is 1, and ln of 1 is 0. So we have 0 on the top. On the bottom, we have x to the negative 1, which is 1 over x. If we replace the x with infinity, you have 1 over infinity, which is 0. So we have 0 over 0. So we could apply L'Hopital's rule. So I'm stating now at this stage, I'm applying L'Hopital's rule. We have the indeterminate form 0 over 0. And let's write the limit. Take the derivative of the top and the bottom individually. Oops. Limit as x goes to infinity. The derivative of the top is 1 over whatever's in the bracket, multiplied by the derivative of what's in the bracket. So the derivative of 1 is 0, and the derivative of x to the negative 1 is negative 1 x to the negative 2. Okay. And on the bottom, the derivative of x to the negative 1 is, again, negative 1 x to the negative 2. This piece and this piece here, they cancel, leaving us with just this term here. So evaluating that term, we get the limit as x goes to infinity. We have 1 over 1. I'm going to write it back as plus 1 over x. And evaluate the limit. So replace x with infinity, we get 1 over infinity, which is 0. So we have 1 over 1. This gives us 1. Again, that's not the final answer. We have to go back to this piece over here. So we found the limit of the exponent. Okay, so the answer we found is just the exponent, so we have really e to the 1, because L is 1, and that's just e. Okay, and the reason why this is interesting because we use this definition already. We use the fact that e is equal to the limit as x goes to infinity of 1 plus 1 over x to the x in an earlier example when we had to prove that the derivative of e to the x is itself e to the x. So this was the property that was used, and now we completed the proof because I assumed this statement to be true. I used the fact that e is equal to this limit and assumed it to be true. Now we proved it, we showed it with L'Hopital's rule, so our proof is in fact complete. Okay, so let's keep practicing. So in this next example over here, example number 4, it says to use L'Hopital's rule to evaluate the limit, and the limit that's given is the limit as x tends to 0 from the positive side of x to the exponent 1 over ln of sine of x. So pause the video, try to attempt this on your own, see if you're able to solve it. It looks intimidating, but using the same procedure that we saw in the previous examples, you should be fine. So let's begin by identifying which type of indeterminate form we have. So we start off by substituting x with 0, giving us 0, and then on over here we have 1 over ln of sine. Sine of 0 is 0, ln of 0 is undefined, but because we're taking 0 from the positive side, it's ln of a number that's so close to 0 but slightly to the right, slightly bigger, which means that we get negative infinity. And 1 over negative infinity is just 0. So we have the indeterminate form 0 over 0, so we have to apply our log property. So let's go ahead and do that. So this is equal to the limit as x tends to 0 from the positive side of e to the ln. So I'm going to right away introduce this and then recopy this in the bracket, giving me x to the exponent 1 over ln of sine x. Okay. We're going to drop the exponent in the front, giving us limit as x tends to 0 from the positive side. We have e, and over here, if we drop the 1 over ln of sine of x, we get essentially 1 over ln of sine of x times ln of x. Okay, because the x is the base, 1 over ln of sine of x is dropped out in front, that's the exponent, giving us this. Okay. Again, exponentials are continuous functions, so we could just jump into the exponent, and we'll deal with e to the l. Okay, our job is to go find L. Let's go ahead and do that. So L is the limit as x tends to 0 from the positive side. And then instead of writing it in this form, I'm just going to write ln of x over ln of sine of x. Right? Because you could think of this as over 1, and you're just multiplying the top and multiplying the bottom, giving us this. Okay. Substituting x with 0, what would we get? We get ln of 0, or a number that's slightly bigger than 0. So that's negative infinity. On the bottom, same argument, sine of 0 or close to 0 is 0, or a value that's slightly bigger than 0, and ln of a value that's slightly bigger than 0 is negative infinity. So we have to apply L'Hopital's rule. We reduced it to a case 1 L'Hopital's rule here. So we have negative infinity over negative infinity, which is essentially just infinity over infinity. So let's take the derivative of the top and the bottom. So we write the limit. Don't forget to write the limit. Derivative of ln is 1 over x, and derivative of ln of sine of x is 1 over sine, times the derivative of sine, which is cos. Now we simplify. 1 over x will leave, but on the bottom we have cos over sine. Actually, what I'm going to do is think of this as a fraction over a fraction. So we have 1 over x, and I'm going to multiply by the reciprocal. So I'm going to multiply by, instead of cos over sine, I'm going to have sine over cos. I was going to introduce cotangent. That's another way of doing it, but I think this is simpler. Because sine over cos, we could just rewrite it as tan. So we get tan over x. So this we've seen already. Now we could apply L'Hopital's rule because it's tan of 0 is 0. On the bottom we just have 0, so we're replacing it with 0. Using L'Hopital's rule, 0 over 0, we have the limit as x tends to 0 from the positive side. Derivative of tan is secant squared, and derivative of x is 1. Substituting it with 0, we get just 1. Again, this is not the final answer. I hope you're still not falling for this trick. This was the answer for the limit in the exponent, which means that the final answer is just e to the 1, or just e. Okay. And now we're done. This is the correct solution. Okay. So let's take a look at our final example. So in our last example over here, we have to use L'Hopital's rule to evaluate the limit, and the limit that's given is the limit as x tends to 0 from the positive side, 1 plus sine of 3x, all that in brackets to the exponent cotangent of x. So pause the video, try to see if you could solve it on your own. First thing we could do is substitute x with 0. Sine of 3 times 0 is 0, plus 1 is 1, and we have 1 to the cotangent of 0. What's cotangent of 0? Well, cotan is 1 over tan, and tan of 0 is 0, so what we really have is 1 over 0, which is infinity. Okay. So we have a case 4 indeterminate form. Let's go ahead and apply our log property. So we take the limit as x tends to 0 from the positive side, e to the ln of whatever we have here, 1 plus sine of 3x, to the exponent cotangent. Let me add a bracket here. That's all inside the cotangent, that's all inside the ln. And now we're going to drop the cotan in front, giving us the limit as x tends to 0 from the positive side, e to the cotangent of x, times ln of 1 plus sine of 3x. Okay. Again, we deal with the limit. E is an exponential function, it's continuous, so we have e to the L. So we pause it, we stop here. Let's go figure out what L is. So L is the limit as x tends to 0 from the positive side of cotangent times ln of 1 plus sine of 3x. Substitute x with 0, what do we get? Well, we have sine of 0, which is 0. 0 plus 1 is 1. Ln of 1 is 0. So we have 0 over here. Cotangent is 1 over tan. Tan of 0 is 0. And then 1 over 0 is infinity. So we're dealing with infinity times 0. But when we substitute x as 0. Okay, so this is a case 2. That means we have to flip one of the functions. Which one do we flip? Well, again, we have ln on top. I'm going to keep it on top. I'm going to flip the cotangent. Why? Because when I bring the cotangent down, it becomes tangent, and that's easy to derive. So let's go ahead and do that. We have limit as x goes to 0 from the positive side. On the top, ln of 1 plus sine of 3x over tan of x. So we apply L'Hopital's rule, because if we plug in 0 now, we have sine of 0 plus 1 is 1, ln of 1 is 0, and tan of 0 is 0. So we have the indeterminate form 0 over 0. Taking the derivative of the numerator, we get 1 over 1 plus sine of 3x, 1 over whatever's in its bracket, times the derivative of whatever's in the bracket. So the derivative of 1 is 0, that's gone. Derivative of sine is cos. We leave what's in the bracket, and then we have to take the derivative of what's in the bracket again. So times 3, because the derivative of 3x is 3. So don't forget that. And then derivative of tan is secant squared. Okay, so let's go ahead and simplify. What we get is don't forget to write your limit as x goes to 0 from the positive side. On top we have 3 of cos x over 1 plus sine of 3x, all that over secant squared. Okay. So this might look confusing, but at the end of the day, all you have to do is substitute at this stage, and it's going to work. So we could simplify it further, but substituting is easier, so I'm going to go ahead and substitute it directly. Replacing your x with 0, we get, on the top here, we get 3 times 1, because cos of 0 is 1. On the bottom, we have 1 plus sine of 3x. So sine of 3x, when you replace x with 0, is 0, plus 1 is 1, divided by secant squared of 0 is just 1. So all we're left with here is 3. And that's the answer for the limit L, meaning that the answer here is e to the 3. This is the final answer. I'm not going to circle this. I don't want you to think this is the answer. This is the answer for L, so the final answer is e to the exponent 3. Okay, so I hope you got that. I hope the video helped, and keep practicing, and I wish you guys the best of luck with your studies.